In this video and the next, I'll be considering invariant structures. Okay, and in this one, I'll be looking at manifolds and geometry in dynamical systems in particular. So manifolds and geometry in dynamical systems. This lesson covers manifolds and phase space, stable and unstable manifolds, center manifolds, normally hyperbolic invariant manifolds, NHIMs, foliations, and flows. So we focus on geometric intuition theory and worked examples to understand these concepts. First of all, what are manifolds? Well, sometimes when you hear words like manifolds, attractors, and all of these things, they are basically things you already know. For instance, attractors are just equilibrium points, basically. So manifolds in their own case, for a manifold, right? A manifold is a space that may be curved globally and it looks locally like Euclidean space. So formally, an n-dimensional manifold M is a topological space such that every point has a neighborhood homeomorphic Rn. Well, like I always like to do, let's look at the idea of manifolds. Manifolds in layman language, in layman terms. Yeah. So what is a manifold? Simply, a manifold is a mathematical space that looks flat, like a straight line or a plane. When you zoom in or on any point, even if it is curved or complex on a larger scale. So it's actually a flat thing, well, especially when you zoom in into it. So a simple example is the Earth. It appears flat to an ant walking on it, despite being a sphere overall. So that's basically the idea of a manifold. So it's locally flat, meaning that wherever you are, you know it's flat, like that every small spot on the manifold resembles normal flat Euclidean space, like one-dimensional line or two-dimensional plane and so on. But it is globally complex in that the overall shape can be curved, bent, wrapped, such as a sphere, that is what the Earth is, a donut shape like torus, or even cylinder. So examples, you have a straight line in a 1D manifold, locally it's a line. A circle is a 1D manifold, locally it's a line. And the surface of a globe is 2D manifold. Locally, it's actually a plane. Why do manifolds matter? They allow mathematicians and scientists to apply familiar simple flat calculations like calculus to complex curved surfaces or high dimensional data. So think of a manifold as a collection of flat maps, like charts, that can be stitched together to represent a complex curved object. So imagine you have a football, I mean the ball itself. If you have the ball and you deflate it and cut it, or you just cut it apart, you stretch it out. So as you move on that flat thing, that is a very good example of what a manifold is. So locally there, it's actually a flat surface, but you can stitch it back together and pump air into it, and it becomes a sphere again. So locally, so that's why we say manifold is a space that may be curved globally. It can be spherical globally, but it looks like Euclidean space, looks locally like like Euclidean space, like a plane or a line. Formally, like I said, an n-dimensional manifold M is a topological space that every point has a neighborhood homomorphic to Rn. Examples, you can have a line, which is one dimensional. You can have a circle, which is also one dimensional. You can have a plane, which is two dimensional. A sphere, which is two dimensional. A torus, which looks like a donut, that's two dimensional. So that takes us to the idea of a phase space. Okay, I think there's something here. Okay. So we talk about a phase space. Consider an autonomous system. I mean, it is time invariant, right? It doesn't depend on time. Don't forget, we are looking at invariant structures. So consider an autonomous system, x dot, which is equal to f of x, for x, which is n-dimensional. So the phase space is R and that is n-dimensional, or you can say, or it's a manifold M. So each point represents a state, right? Then each trajectory is a curve on the manifold. So that's talking about, so the phase space is Rn, right? And each point represents a state, and each trajectory is a curve on the manifold. And that takes us to the idea of linearization. Okay, let x star be an equilibrium. We have f of x star to be 0. So linearization means we have y dot equals d of f x star multiplied by y, where y is x minus x star. So eigenvalues of the derivative of f of x star determines stability. I mean, we've done this a couple of times, that you have a system, you use the Jacobian method to linearize, you find the eigenvalues, which then determine the stability for of each equilibrium based on their eigenvalues, right? So, and then we go on to hyperbolic fixed points. We've talked about this also before. So an equilibrium x star is hyperbolic if the real part of the eigenvalue, if it is a complex eigenvalue. Well, of course, we already know that all numbers are complex technically, because you can write every number as a plus bi or a plus ib if you like. So if, for instance, one is 0 plus, I mean, one is 1 plus 0i, and 0 itself is 0 plus 0 if you like. So an equilibrium x star is hyperbolic if the real part of the eigenvalue is not 0. If the real part is 0, then it is non-hyperbolic. So, and if that happens, so an equilibrium x star rather is hyperbolic if the real part of lambda I is not 0 for all eigenvalues lambda I. So the classification will now go like, so for that real part, now if it is less than 0, it is stable. If it is greater than 0, it is unstable. We've looked at this several times. I've even explained how to compute all this. So then we talk about stable and unstable manifolds. Again, don't disturb yourself. A manifold is stable when the eigenvalue is less than 0. That real part is stable, right? And a manifold is unstable if that real part is greater than 0. So when you hear manifold, we are basically still talking about the same thing, except that now we are using a big word, so to speak. So let phi sub t of x be the flow, for instance. For the stable manifold, we have that Ws, Ws talks about stable of evaluated at x star is the collection of all x such that phi sub t of x, moves towards x star as t goes towards infinity, basically. So it's like the equilibrium point. So the system is moving towards the equilibrium point as t goes towards infinity on the positive side, and then that gives you a stable manifold. For the unstable manifold, that's power u of x star is a collection of all x. So phi sub t of x moves towards x star as t goes towards negative infinity, basically. So that's how we define that right there. And then we have stable manifold theorem now. If x star is hyperbolic, that is the real number part of the eigenvalue given by s star is not 0, that means it is hyperbolic. If x star is hyperbolic, then the stable manifold and the unstable manifold do exist, and they are smooth manifolds, and then they are tangent to eigenspaces, of course. So they are stable and unstable based on the fact that the eigenvalue for stable eigenvalue is less than 0, for unstable eigenvalue is greater than 0, and they are smooth manifolds like that, and they are tangent to eigenspaces like that. So it means you can find corresponding eigenvectors. So you can uh yeah, you can actually write them as they are tangent to eigenspaces exactly. So locally, you have nonlinear dynamics looking linear like that. Nonlinear dynamics looking linear, especially when you come up with the idea of linearization, as we see here. Imagine we have a saddle point here. You have a system x star equals x, y star equals minus y. The matrix is simply for x, you have 1, y is not there, so you have 0. For second one, x is 0, y is minus 1. So this is a diagonal matrix. So the eigenvalues are simply 1 and minus 1. This is positive, this is negative. Stable manifold, unstable manifold, basically. So 1 is unstable manifold, minus 1 is stable manifold. And because you have the two eigenvalues, one is stable, one is unstable, automatically that gives a saddle point. So the geometry is something like you are moving towards it, but when you get close to it, there's a shift away from it because it's a saddle. So to do the general solution of that based on the eigenvalues now, x of t, x, this is the x-axis now. That's the positive one. So x of t is x naught e raised power t, and this is the minus one corresponds with the y-axis. So y of t is y naught e raised power minus t. So for the stable manifold, basically, we have the stable manifold is corresponding to y. So we have 0, comma y. For the unstable manifold, you have x, comma 0, basically. So that's what the whole idea of manifold is about. And then we can represent that using Python as we see like here. So you have Of course, x, you're taking this from minus 2 to 2 on both x and y axis, and then you have x and y, you do the mesh grid. So you have u is x, v is minus y. So just like the whole idea of x dot is x, y dot is minus y. So that's what's happening here. And then we do the plots, we plot the stable and unstable like that. So this is 0, 0, minus 2, 2, minus 2, 2, 0, 0, like that. And then we just have this. This may take a bit of time because it's the first code I'm running in this session. So that usually takes a little bit of time. Okay, it's coming on. Yeah, that's what we have here. So we have a saddle point. We have saddle point manifolds there because we have on the Y part, we have a stable manifold. On the X part, we have an unstable manifold. So as a result of that, every flow that is coming, it gets towards the saddle and then it shifts away because it's actually a saddle we're dealing with here. So let's go to talk about center manifolds. So we've talked about stable and unstable manifolds, right? We also have center manifolds. So center manifolds occur when we have non-hyperbolic equilibria, right? So for center manifolds arise when the real number part of the eigenvalue is equal to 0. So in that case, you cannot really classify the equilibrium producing it as either stable or unstable. So you can't classify. So center manifolds arise when the real part of the eigenvalue is 0 for some eigenvalues. So even if it happens for one eigenvalue, you're going to have a center manifold. Okay. So linearization cannot determine stability in that case because of that zero thing. And then we now need to use center manifolds to reduce dimension. So we can then have a subspace decomposition which splits the real number, the n-dimensional real number system into the stable part, the center, and then the unstable part, like that. So that's the real number system is now broken down into those components. ES is stable, EC is unstable, and EU is EC is stable, ES is stable, sorry. EC is center and EU is unstable. And then talking about the center manifold theorem, we then have this that there exists an invariant manifold WC such that the tangent to EC contains long-term dynamics, which is locally attracting, and dynamics reduces to Z dot equals GZ, where Z belongs to the invariant manifold, right? So we have a good example here. Imagine that you have this system x dot equals y minus x squared. So on the x part, right, you have okay, okay, I think we have a kind of jump right here. So I may need to write x dot is y minus x squared, y dot is minus y. Okay, x dot is minus y minus x squared, y dot is minus y. So if we want to do the Jacobian of this, right? So Jacobian of x, okay, before we even do Jacobian, we have to solve the equilibria, right? So we go for equilibria. So for the equilibria, what do we get? We have 1 y minus x squared. Okay, well, we can start with the simple one. Minus y is down there. So y minus y equals 0 simply means y is equal to 0. So conclusively, y is 0. On the other hand, now we have y minus x squared, okay, equals 0. So because we already got y to be 0, we have y minus x squared is equal to 0. So that means that, this implies that minus x squared is equal to 0. And that simply means x is equal to 0 twice, okay? So as a result of that, we have just one equilibrium point. We have x star, y star, okay, which is equal to 0, comma 0. So we have that, right? So now we now get to linearize. So for linearization now, we have j of x, comma y equals, so differentiate this expression with respect to x, we get minus 2x. Is it minus? Yeah, minus 2x. Minus 2x because this is minus x squared, right? Differentiate with respect to y, we get 1 here. Okay. And then coming down, we differentiate this with respect to x, we get 0. And then we differentiate with respect to y, we get minus 1. Okay. So if we then evaluate the Jacobian at 0, comma 0, which is I mean, now we want to do Jacobian evaluated at x star comma y star now. That is j of 0, 0. And that is simply minus 2 into 0, 1, 0, minus 1. Okay, so that means we simply have the Jacobian at the equilibrium is 0, 1, 0, minus 1. So what do we have? This is, we can just, we know the, because this is a triangular matrix, we can just know that the eigenvalues, lambda 1 is equal to 0, lambda 2 is equal to minus 1. And once lambda 1 is 0 like this, once lambda 1 is 0 like this is non-hyperbolic, non-hyperbolic. Okay, so we can't use linearization in this case. We cannot determine the stability. Of course, for this other one now, we have stability for this particular minus one, but the other one is non-hyperbolic. So there's nothing. So we have to look for better ways of handling that. So we have 0 and minus 1, and that is non-hyperbolic, just like I said. So, and what we can then do is to go and use the manifold idea. So, and for the manifold, we assume that y is equal to h of x. All right, y is h of x, and that is the same thing as ax squared. Because linearization has failed, so we go to the second order. So y is equal to h of x, which is ax squared. And for the invariance condition, what we are then going to do is to say h prime of x multiplied by x dot is equal to y dot. Okay. I hope maybe I need to write still. So because of the non-hyperbolic nature of the eigenvalue we got there, right? So we assume that y is equal to h of x, and that is ax squared. That means y dot is equal to h prime of x, differentiate h prime of x, and we have 2ax. So we have this now. Okay. So with that in place, we then move on to another thing. So yeah, so that is h prime of x times x dot. Okay, okay, okay. Now I get the gist there. So, this is, so if to get y dot, we're differentiating with respect to time, right? So it means that this is going to be an implicit thing. So we have h prime of x multiplied by x dot to balance it. It's more like saying dh dx times dx dt. That's the deal. That's what is exactly happening there. Because y dot is the y dt. So the y dt, if the y is h of x, so then the y dt has got to be h prime of x times h times x dot. Okay, and that will be equal to when you differentiate this. Aha. Okay. I think we can then follow this through. So, this is, so because we have this, right? So that means we can then have, so it means we have y dot equals h prime of x straight off is 2ax, but then we have x dot, okay? We have x dot, but then x dot is already given. We have x dot was given initially as y minus x squared that we have here, like this for the x dot. So, so that means we have, like we said, x dot originally is y minus x squared. Okay. So that means y dot is equal to 2ax into y minus x squared. And then don't forget that this y minus x squared now, this y has already been given as h of x. Okay. So y dot is equal to 2ax into h of x. Yeah, this is h of x, but it's still y, right? So this is ax squared, right? This is ax squared minus x squared. We have this kind of thing here now. So what do we do then? So we need to, I think we need to find the value, we need to get a. So how do we find a here? Um, we need to get the value of a. So we can then compare, we know y dot from the beginning to be minus y, right? So this whole thing, so knowing that, I guess I may have to change the marker. Knowing that y dot is equal to minus y, so we can say that um, this is, and of course, that means y dot is equal to minus y is h of x. I mean, y is h of x, right? And h of x, so y dot again is equal to h of x is 2a, I mean, it's h of x is ax squared, yeah? H of x is ax squared, like that. So, and we need a from that situation. So, but y dot now is 2ax into x squared and all that. So we have 2ax into ax squared minus x squared is equal to minus ax squared. So in short, we just need to find a, well, maybe to make life easy, I can just cancel a out first here, and then I can divide through by x. One of this will go. So I have 2ax squared minus 2x squared equals minus x. Okay. So this is like we still divide through by x. Okay, so we have 2ax minus 2x is equal to minus 1. So our goal is to find the a at the end of the day. So this is x into 2a minus 2 is equal to minus 1. Mm, so I think I'm doing something here that I should pay attention to. So here, in short, we have this is x dot, right? So we have h prime of x times x dot equals y dot. And then h prime of x is this. X dot already. X dot is y minus x squared. Okay. And y is h of x. So h prime of x, hx minus x squared equals minus hx, like this. So if we solve this system now, that is what is giving us this a equals 1. Maybe I should still continue. Maybe I should still continue because we need to find a. Mm, so I hope I've not messed up anything here. Or maybe I should just jump. I should take what I have over there and just transport it here and continue with that calculation. Um, this is taking a bit of time. So we have h prime of x. So the whole thing is starting from y equals h of x equals ax squared, right? So we have h prime of x. Okay, let me start afresh, right? So we have um let y be h of x, and that is ax squared. So that means that y dot, okay, is equal to, when we differentiate this, we have h prime of x, but because we are dealing with time and not x, so we have to balance it up with x dot. So it's more like saying dy dt, because the y is already h of x. So the y dt is now the h dt, or better still, the h dx multiplied by the x dt. So that's the way to balance. That's why we have this here. And that is now equal to, okay, maybe let's just leave it alone first. We have this like this, right? But from the original expression, we know that x dot was y minus x squared and y dot was minus y. So we are also going to refer to this now. So with this in place now, we have h prime of x dot equals equals y dot, just transferring this to the other side equals y dot, right? So with that now, we then have so we can then replace this and this. we have h prime of x into this x dot is y minus x squared, right? So that's y minus x squared, and that is equal to minus y. Okay, but we have replaced all that with h of x. So that's like h prime of x into h of x, y is h of x minus x squared equals minus h of x again. So, and what are we looking for here? We are looking for this a. But we know h of x is ax squared, right? Trying to let's tidy up as much as possible. So we have h prime of x, h of x minus x squared, h prime of x is equal to minus h of x, you know? Then, what else can we do here? So we can bring this over. So we have h prime of x, h of x minus h of x. I mean, this minus h of x becomes plus h of x minus x squared h prime of x. All of that is equal to 0. Okay, so h of x is common now. H of x into h prime of x plus 1 minus x squared into h prime of x equals 0. So what do we do? H of x, we know is a. Okay, maybe I should change at this point. Okay, h of x is ax squared into h prime of x is actually 2ax plus 1 minus x squared into h prime of x is also 2ax, and that is equal to 0. So here x squared is common, so we have x squared into um 2ax 2ax like that. We have 2ax plus x squared is common, right? Plus a. Then x squared is already out here. So we have minus 2ax. Okay, now I think it's making sense like this. So 2ax cancels 2ax. So we have mm, we have to be careful here. What's happening here? So ax squared, right? So we have 2ax. Okay, I guess I need to go step by step. We're looking for a, basically. So we have so this is like so this is x squared out here into a into 2ax plus 1, yeah? Minus x squared is already out into 2ax like this. All right. So I then have um x squared into 2a squared x plus 1 minus 2ax. All of this is equal to 0. Okay, now I think this is the deal. So, of course, clearly x squared is equal to 0, and we don't need that. Or 2a squared x minus 2ax plus 1 is equal to 0. So that we then have, what do we do here? 2a is common, or should we just take out the x? X into 2a squared, all right? X into 2a squared minus 2a plus 1 is equal to 0. Plus 1 is equal to 0. So, do we compare now? Constant for constant. I think we have to do that for x component now. Talking about x, on the left-hand side, the coefficient of x will be 2a squared minus 2a. And on the right, we have 0. So that means we have, so a is common. So we have a into 2a minus 2 equals 0. So again, we have a to be 0, or 2a minus 2 is equal to 0. So 2a is equal to 2. So a is equal to 1. Imagine that's the trouble we've been going through this for. So for the constant part now, so for the constant part, we have 1 on the left, 0 on the right, which doesn't make sense. But finally, we have got our a to be equal to 0. So in this case now, it means that we have y, which is h of x, which is actually ax squared, And since A is 1 now, so we have 1 times x squared, which is x squared. So basically, we now have y to be equal to x squared in short. So if we do the system again, it means that the original system, which was x dot, right? The original system, which was x dot, which is y minus x squared, we then have x dot. So this implies that we have, now y is x squared, so we have x squared minus x squared. Okay. So this implies that x dot is equal to x squared minus x squared. That means x dot is now equal to 0. We have this. Then on the other hand, y dot, which was equal to minus y, implies that y dot is equal to minus x squared. So that's minus x squared. So the system, what we have done here is to translate the system since linearization could not do it. So finally we have x dot equals 0 and y dot equals minus x squared. So this is the new system we now have to work with. Okay. And we can see that okay, so we finally discover that the center is y equals x squared, because x squared, if you equate this to 0, this is just a center. It gives us 0. So y is x squared. So we then have the reduced system. On the center, we have x dot equals x squared minus x squared equals 0. So so like this. So then this is the equilibrium. For the equilibrium, so this now gives the equilibrium state. X dot equals 0. Just that. So it's a center like that. So that's all the plenty math we've been doing. Yeah, so finally, maybe not finally, we talk about another idea, which is the normally hyperbolic invariant manifolds, NHIMs. An invariant manifold M is normally hyperbolic if the norm of d phi sub t, uh, you know, multiplied by the the okay, evaluated as n also is far, far greater than this other side of the expression. So that's normal contraction dominates tangential motion. So normal contraction dominates tangential motion. And then this talks about, we then have the slow fast systems. Um, this is a quasi, there's a method, this is called quasi steady state something something. So talking about slow fast systems now, we consider this system now x dot and y dot, they are supposed to be normal together, right? But because of this epsilon here, this this epsilon x dot, f of x now becomes a faster system compared to this. So we now have slow fast systems like that. So with 0 less than epsilon, and epsilon is far, far less than 1. So it makes this is it faster or slower system now. So the critical manifold here will now be f of x comma y equals 0, because, and this is often NHIM, which is normally hyperbolic invariant manifolds. Okay, so and then we then have the Van der Pol system, which follows that kind of idea, that you have x dot equals y minus x cubed over 3 plus x, and y dot is epsilon multiplied by minus x. So for small epsilon, slow manifold exists. Okay, so this epsilon makes this f part very slow. Okay, um, and then we can have this Python code to take care of that. If you take epsilon to be 0.01, and of course we have this other system the way it is, we have the slow manifold right there. So this is how this goes. So what if we change this to 0.01? It's even slower. Okay, think it's done. It's even okay. Maybe no serious change. What if I make it very small? Okay, the epsilon, because so you see what's happening here now. So what if I make it 1? What if it is 1? Okay, so we have something like this. So it's just it's doing some kind of stretching out like that. So we have this now. Yeah. So then we go back to talk about flow. That's part of the things we said we wanted to talk about. Of course, we talked about flow, right? Right from the beginning of when we're describing what a dynamical system looks like. So talking about flow now, for x dot equals f of x, the flow can be said to be phi sub t of x naught, that is evaluated at the initial condition, is actually equal to x of t. And then the properties are that the initial flow is the identity, and then Flow at time after some time is the interaction of time and space like this. So that was part of the definitions we had from the very beginning. And then that takes us to the idea of foliation. So a foliation decomposes space into leaves. So leaf, like when you hear folio, right? Uh, um, exfoliation, things like that. So foliation decomposes spaces into leaves. So you have the manifold into the union of several leaves, L alpha, like that. So you have L alpha, leaf one plus leaf two. I mean the union that's leaf one union leaf two union leaf three union leaf four and so on. So each L alpha is a submanifold. You can think the pages of a book, right? So each page of a book, you see that as a kind of leaf. So talking about stable foliation now, near a hyperbolic set, you can say the manifold is the union of all stable, all stable leaves or all stable components like that. So each leaf can then be seen as a stable manifold in that case. So a very good example we can see here, if you imagine the system x dot equals x, y dot equals minus y, clearly the eigenvalues are 1 and minus 1. That is a saddle kind of. So for stable foliation, let's say x is equal to c. Of course, stable foliation, we know because this is the stable foliation happens. Stable foliation should be for y, right? Okay. Stable foliation x equals c and unstable foliation is yc. But of course, we know the eigenvalue here will make it stable. So it's like, are we reversing it? So we are decomposing the space into leaves now, both stable and unstable. So, and for all that, now we can just come here and have foliation plots to take care of that. So the stable is red and the unstable is blue. But of course, by eigenvalue, x is the unstable manifold, while y is the stable manifold. So let's see what the plot looks like if it's going to agree with that. So we already know that x should be unstable. So the x-axis has the unstable blue. Yeah, you see the blue running across the x-axis, and then the red across the y-axis, which is supposed to be stable like that. Okay, so we have those foliations like that. And then the unified picture at the end of the day is something like this. You have the phase space. From the phase space, you have the equilibria. From there, you can see stable or unstable manifolds or center manifolds. Stable if eigenvalue is negative, unstable if eigenvalue is positive, center if eigenvalue is zero. And then if eigenvalue is zero, you then move on to the next step. So it's like the how you flow. So if you have center manifolds, then you can then to look at non-invariant sets where you now do NHIMs, and from there you can look at the global geometry, and under that you have foliations. So comparing all of these ideas together, you see that for stable manifold, the purpose is convergence and usage is for hyperbolic points. Center manifold, the purpose is reduction for zero eigenvalues. NHIM is persistence, talking about slow fast systems. And for foliation, you have a global structure for hyperbolic sets. And flow is for time evolution for all systems. So for applications, where do we apply all these manifolds and geometry in dynamical systems? These tools are used in fluid mechanics, climate models, neuroscience, robotics, celestial mechanics, and control theory. They allow dimension reduction, stability analysis, bifurcation study, and chaos detection. And the learning path for this whole thing, for the recommended order, check for linear systems, check for stable manifolds, if check for center manifolds. If they are center manifolds, then think about well, you can do bifurcation theory, do the NHIMs, check hyperbolic dynamics and ergodic theory, right? So ergodicity, simply, I think I talked about the idea of ergodicity previously, that it is knowing that if you toss 1,000 coins once, it's the same thing you get when you toss um a coin 1,000 times, that kind of thing. Okay. So you have your practice problems here. Consider the system x dot is 2x minus y. This find the equilibrium. You just solve simultaneously. Compute the Jacobian. We know that already. Then classify the stability. Classify the equilibrium. Determine the stability and all that. The stable and unstable manifolds. So the kind of thing we did just now. So you want to watch for that. Then 3 and 4. You have saddle with coupling. Of course, clearly this is the eigenvalue here is 1, the eigenvalue here is -1, so that's the saddle. So you want to linearize at 0 because, of course, x is 0, of course, y will be 0 too. So same thing like I did before. Center manifold reduction, you want to try this also. Then 5 and 6, you have 0 eigenvalue. Of course, clearly, you have the equilibria will be 0, 0 also. So for x dot here, you have 0 eigenvalue because if you evaluate at 0, you get that. And for here, so slow fast, we have the epsilon thing. So you want to find a critical manifold from what we've talked about just now. Then for NHM verification, you want to try this out too. So you have this identify invariant manifolds. Then for flow properties, check this out too. And lastly, you have the flow foliation structure from these things and numerical manifolds. Yeah, let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I must thank you very much for doing that. If you haven't, the question is, what exactly are you waiting for? Go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you some special privileges, like getting to see some videos first, or being the only ones to see some videos as members. And of course, we can hang out together. I can to discuss whatever interests you on this channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.